Hi, everyone. My name is Fedorenko, and I'm co-presenting with Jacob Andreas on this language and thought mission. Very happy to be here. Oh, is this okay? Okay, so language is this incredibly powerful thing we have which allows us to share the contents of our minds with one another. And we can do it in the moment, like I'm doing right now, but also across millennia, transferring cultural knowledge that accumulates across many generations. The fact that language can and often does reflects our mental states has led to a lot of confusion about those things being kind of one and the same. It turns out, however, that in the human brain, language and thought are distinct. What kind of evidence do we have for that? Well, it comes in two flavors. One thing we can do, this is a more modern approach, is we can find individuals' language brain areas. We can do this in a few minutes of scanning. And then we can simply ask people to do various thinking tasks. We can ask them to do some math, or to solve a logic problem, or to engage in physical reasoning, or reasoning about others' minds. And then we can ask, how much are these language areas responding when people are engaging in these various things? And we find that the language areas are actually almost silent when you're engaging in all of these complex cognitive reasoning tasks. The other approach is more olden days. We've learned most of what we know about the brain from early work in neuropsychology, which is looking for cases of dissociations in patients who sustain brain damage. So we're trying to look at here in individuals with language problems, with aphasia. I'm showing you just 3 brains of individuals with really severe aphasia, with a huge portion of the left hemisphere affected typically by large stroke. And again, we can ask these patients who are severely impaired in language, they can't produce or understand a single word, never mind a sentence, can they still think? Can they play chess if they play chess before their injury? Can they drive cars? Can they reason about other people's minds? And again, it turns out that remarkably they can. So language can then be defined in this relatively circumscribed way as a system of conventionalized symbols that we can use to convey very detailed meanings to others. Thought is harder to define. It encompasses a whole set of different kinds of things, from concepts, which are basic building blocks of thought, to various kinds of reasoning, some of which you've already heard in other talks, like reasoning about the physical world, reasoning about the social world, very abstract kind of reasoning that we do when we solve these standard kind of IQ puzzles on geometric patterns. And one thing, and this trying to understand whether different kinds of reasoning rely on the same machinery or not is still very much an active area of work, but we've definitely learned that there's a few distinctions that exist. And so in humans, then, language and thinking appear to be independent of one another, and in the space of reasoning, there's many distinctions that have already been discovered. One big focus in ongoing work, this is in collaboration with Nancy and a few others, is trying to understand how the language system works together with all these other systems. Because language, like I said, is this very powerful thing that allows us to teach each other totally new things, right? Accumulate knowledge, share social knowledge, and so on. And so we're trying to think about when different kinds of information come in to our brain through language, how do we route information to the relevant brain system that can then perform downstream reasoning computations? Now, in the dominant paradigm in AI has been quite different in that basically this early wave of neural network models has tried to bootstrap everything from language, right? And it turned out that that's a really powerful approach, and that's why people have been investing so much money and effort into kind of pushing this approach as far as it goes. But it turns out that you can learn language pretty well from language statistics, contra some older claims that language requires explicitly symbolic representations. Turns out actually learning linguistic syntax is not a problem. The problem arises when you're trying to make everything work just based on language alone. Oh, and I should have mentioned that not only is it easier to learn language, but these models of language, these large language models, the wave of models trained on text alone, are actually really good predictors of responses in the language brain areas, as Jim showed you. So I will pass the mic to Jacob in a second. I'll just say that on the brain side, there's a few things that we're working on. A lot of it is in intense collaboration with Jacob's group and others in the department. So on the language side, even though you can learn language from statistics alone, kids require a lot less data than models, so we're working on developing more developmentally plausible models that learn from audio input, not pre-tokenize vast amount of text. Haley Olson will have a poster on this in the session. And then a lot of our work is actually on the side of thought these days, trying to understand and refine the ontology of thinking, which kinds of reasoning require their own specialized machinery and why. In current models that are these end-to-end systems, we're trying to evaluate these models, trying to understand what kinds of things are particularly challenging for them. To the extent that we look inside these models, do we see any modularity emerge just in these systems where we didn't build anything in, but maybe we find that some kind of things just naturally segregate by virtue of the different computational demands that these different tasks require. And Ben Lipkin and Andrea DeVardo have been working in that space. And then in line with what others have been talking about, we're also trying to develop alternatives to these models. And Jacob will tell you a lot more on that, where you don't just try to bootstrap everything from text, but you imbue these language models with other kinds of capacities and see if they do much better in the hope of building these integrated models of language and thought in both humans and machines.
Cool. So picking up where Ev left off, let's talk a little bit more about the AI side of these things, right? And as Ev was saying, the computational models that we have today, which you can think of as basically fancy autocomplete models that were trained on a huge amount of text, work quite differently from all of the pictures of the brain that we've seen today, rather than sort of having these nice sort of modular structures and explicit, processing machinery for explicit tasks. We have just one big chunk of neural computation that does all of language processing and all of the sort of thinking that needs to support that language processing. And as much as these models have gotten very good at generating fluent text, there are still many ways in which they fall short when you evaluate them on these tasks that require more sort of intensive kinds of thinking. And so, I think the big challenge here, both on the scientific side and maybe on the engineering side of this quest, is to figure out then how to think more carefully about the interface between language and thought in computational systems, and how to build systems that have the kind of flexibility and richness and the ability to be trained on sort of naturalistic modern, or the kinds of data sets that we have for training modern language models, but that are good at thinking in the way that people are good at thinking without, sort of starting to become bad and at language in the way that, sort of 10 years ago, even language models that we had were bad at language. And so to sort of put up our North Star for this project, it's something like the following. Imagine that we had the kinds of, a kind of system that looks like ChatGPT or any other language model that you interact with nowadays that can have conversations in natural language, but whose internal mechanisms look not like the kinds of models that we have right now, but that actually look like something like the human mind or the human brain, and that have the kinds of structures and the kind of interfaces that support both thinking and doing language. So to talk a little bit about some of the work that we've done in that direction, I think if we really want to build effective models that mirror what we understand about the structure of language and thought in humans, we need to think more carefully about the sort of interface between language and thought in these computational systems. And so this requires both understanding what these interfaces look like in the kinds of models that we have today, the kinds of algorithms that you can implement inside something that looks like a transformer language model, and maybe the kinds of algorithms that you can't implement, and then figuring out how to build more expressive versions of these models that are, don't necessarily have the same kinds of computational constraints. And so on the first point, one of the big focuses of Quest work, especially from my lab and especially work by my grad student Belinda Lee, has been just sort of understanding basically the architecture of thought in language models, understanding what kinds of procedures they use for doing things like state tracking tasks, things that require them to simulate physical situations, things that even require them to reason about themselves and their own knowledge. And what I think we have now is actually a pretty detailed algorithmic picture of what goes on in many of these kinds of important tasks inside models. And I think the sort of important high-level lesson here has been that these models are quite limited in many respects, that they're computational constrained. There are lots of important kinds of computations that you can't get them to do that we think are important for thought. And they're sort of representationally constrained in the sense that the models that they build of the world internally, the ways in which they represent the world, don't necessarily cohere into sort of a picture like the one that people have. And so on the other side, another big piece of our effort, and this has been a sort of project really across the Quest with a bunch of PIs, including Josh as well, and our former grad student Leo Wong and Gabe Rand, is to figure out alternative ways of building models that can solve these harder problems. And the sort of big idea here, building on some of the themes that we saw before in the perception piece of this, is to externalize some of those hard computations, right? So there's this sort of long tradition in work in cognitive science on the language of thought, right? The notion that thinking might have language-like structure underlying it, even if it doesn't look exactly like natural language. And one of the consequences of this in sort of modern language processing systems is that you can actually adapt them relatively straightforwardly to generate externalized symbolic representations of computations, of plans, of sort of thinking in a general way, on top of the same substrate that we use for training language models as they exist right now. And so you can build models that basically think not by generating text directly, but by external, sort of outputting symbolic programs, probabilistic programs even, that you can run in order to compute the answers to whatever questions users have asked you. And so there's a long line of work from a bunch of people here doing this. What's cool is that you can use this not just for sort of answering questions in natural language, but also language that involves reasoning about either sort of real or imagined physical situations. And sort of mirroring some of the slides that Jim showed in his piece of the talk, these models are both good at predicting sort of human judgments on a bunch of tasks that involve reasoning under uncertainty, and they're actually good at building sort of real-world useful systems that can learn from very small amounts of experience, that can solve planning problems, that can infer what kinds of goals human users want, and all that. So here's a system that learned from a very small number of demonstrations that what the user wanted, right, the model of the world that it should be building needs to pay attention in particular to the relationship between this wet rag and the book. The other sort of piece of this, right, if we have the ability to build things that look like language models, but that can externalize their thoughts as programs and run those, we would like more efficient ways of training these models in the first place. As impressive as modern language models are, they're trained on orders of magnitudes more language data than human learners. And so a really important scientific challenge here, if we want to build these systems in a way that's sort of like really informative about human cognition, really plausible, is also to figure out how to train them on more sort of human scale data sets. And so our former postdoc, Changshu Zhuang, who was now one of the founding members of this new Meta Superintelligence Lab, has spent a bunch of time thinking about these kinds of questions, and in particular coming up with ways of training language models that can learn not just from text, but from text sort of situated in perception and action and social situations. He was focusing specifically on sort of vision problems and built what we think is the first example of any language model that actually got better at sort of next token prediction in text tasks alone by being exposed at training time to sort of perceptual grounding as well. And then, a sort of important sort of overarching piece of this is that we need also tools for measuring our progress towards building more human-like models of language processing and language understanding, and especially systems that can sort of generate language plausibly in the service of some of these more complex thinking tasks. And so we had a big benchmark that came out earlier this year, led by our postdoc Anna Ivanova, on exactly this sort of various kinds of problems that require generating text about complicated underlying situations that require modeling the world, and finding here, both that there's sort of, an interesting distribution over human responses to these problems, but that current computational models that we have fall very, very far short of human performance on this category of problems that we should think of as involving sort of language-informed thinking, language-informed reasoning about the world. And I think Josh is going to talk a little bit more about this benchmark later on. And so just to sort of wrap up with this North Star again, again, what we really want to build here is a system that can take the same, have the same kinds of conversations that we have right now, but where the mechanisms generating those conversations are not whatever sort of weird large language model-like things get learned, but instead things that also teach us something about human cognition. And I think we've started to make progress on that, both in terms of figuring out what the structure of those computations ought to look like, and what kinds of training data and learning algorithms we need to build those models in the first place. Thank you.